All right, so I wanted to do a video of me going over the questions and problems that you had at the end of class yesterday because of the fact that we didn't get to go over them together in class. So the first few questions deal with the concept of how we would add vectors in a more visual or graphical way. And remember that my goal is just for you to have a sense of what two vectors added together might look like. And so in this first one, we might be thinking of the head to tail method. And so in the head to tail method, the idea is you draw one vector, the pointy end is the head, and then once you draw that first vector with the proper magnitude and direction, you start at the head of that vector to draw the second one. When we look at the two vectors and how they're added together here in these choices, we notice that for choice A and B, these are actually tail to tail. And so they're not using the head to tail method. And so that's not how we would add them. Now, in C and D, they are using the head to tail method. Now, the way that they did that is they started with vector B and then added vector A, if we think about how we would go about the process. And that's okay, because A plus B is the same as B plus A. It's just like when you add numbers, it doesn't matter the order. Now, not everything we do with vectors can be switched like that. Remember that in math, we call that the commutative property. Now, if we look at the choice C, we have B, and then at the head of B, we draw A. And then the way that we finish to find the sum of those two is we start at the tail of B, and we go to the head of A. And this becomes A plus B. And that's exactly what they've done in choice C. Notice in choice D, this is drawn in the wrong direction. So this is not the vector. The yellow dotted line is not the vector for A plus B. So our answer here is C. Now these two, this picture is asking us what is B minus A. And something that I told quite a few groups is we might want to think of this as B plus minus A. And what is minus A? It's the same magnitude as A, but it's in the opposite direction. And to be honest, I found it easiest to think about how I might do that for each one of these, how I might do the head to tail method of B plus negative A, and then use that idea of how I might figure out what the sum is. And so in A, I'm just going to kind of write it. I'm going to draw, sorry, it shouldn't be A. In choice A, I want to just draw it how I would do that if it was B minus A. So I would do B, this would be B, and then minus A would look something like that. And then this would be the sum, B minus A, would look something like that. The things that I'm noticing is that the sum of B and minus A, I expect it for this one, it's downward and kind of to the right. And that doesn't look like what we have here, so I don't think that's correct. For B, again, I just found it easier to redraw these. So this is B, this is minus A, so I'm using the head to tail method, and then this is B minus A. And I actually am liking that one, but just for to practice, I'm going to do C and D the same way, just to practice what I'm doing, the head to tail method, in a very kind of informal, just sketching way. This would be B, this would be minus A, and this would be B minus A. And that doesn't at all look like C. And then finally D. D is really the same sort of scenario as C. And again, I don't see that this matches the way that they drew it. And so I've concluded that my answer is B. Again, what I found was a useful way to do this is that subtracting a vector is the same thing as adding a negative vector. And a negative vector has exactly the same magnitude. It's parallel to the original vector, but points in the opposite direction. All right, now we get into some of the questions asking if we can figure out how to find components of vectors drawn in the XY plane. I would refer to this that we're drawing the vectors showing their magnitude and direction. It's a very common way to represent a vector where you're drawing it in the XY plane. You have it labeled in terms of how long it is, and then you also show an angle that it makes with either the X or Y axis. For both of these vectors, they've drawn the angle relative to the Y axis, which is not the standard way we do it, and that's why we have to always be careful that we think about the definition of sine and cosine and the fact that they're related to adjacent sides and opposite sides, for adjacent for cosine, opposite side for sine, and thinking about which one we want to find. So in this problem, we're asked to find the x component of vector D. I want to just take a moment to draw the two components. So this would be dy, and this would be dx. And I notice that dx is opposite the 53-degree angle. And so that tells me that I want to use the sine of 53 to find dx. So dx would be written as d times the sine of 53. And when I use that small angle 53, if I took the sine of that, I would get a positive value, but I can see from the picture that the x component is negative, and so I want to put that negative sign in there to make the x component have the correct sign. And so this would end up to be minus 10 times the sine of 53. So I've figured out how I would write the x component. And now I look over here and see where my correct choice is. And it's D. Now this is a problem, I gotta admit, this one gets me every time because I make the assumption that they have put the XY plane in a standard orientation. But look at what they did. It's so rude. They made the x-axis vertical and the y-axis is the horizontal. And where it is labeled, we would assume that that was the positive direction. I wouldn't do that to you, but it's good to be careful and to notice details, so I guess we'll take it at that. And then now that we've noticed this non-standard orientation of the coordinate axes, I'm ready to read this question and try to find the answer. We're looking for a vector that has a negative x component and a positive y component. So the negative x is going to be down here in these two quadrants because, again, I mentioned that where you label the axis is always assumed to be the positive direction. So the positive direction for x is denoted to be up. And then using that idea, the positive direction for y is, I've just circled, that's to the left because that's where that's labeled. And if I look at where my two circles overlap, I see that vector D has a negative x component and a positive y component, and that becomes my answer. This is another problem where we have to be careful because of the fact that the whole coordinate system is kind of put at angles, and again, it's a little less standard in terms of how it's oriented. So, they do help us here where they're showing us that that vector right there would represent the x component of vector E. This is vector E right here. And that's positive. And they also they tell us that the y component of vector E is also positive. And notice also they're using the angle beta. You're going to learn a lot of Greek letters in physics. That's one of the perks. And it's labeled relative to the y-axis. Again, not the standard way to measure an angle. We're used to sort of assuming our angles would be measured relative to the x-axis. And so when they're measured relative to the y-axis, we have to be especially diligent in thinking about the definition of cosine and sine, the fact that the cosine of beta would be the adjacent side over the hypotenuse, and that the sine would be the opposite over the hypotenuse. I think that these definitions, your SOHCAHTOA, is really helpful to help you write components correctly. And so the y component is adjacent to angle beta, so this is going to have a cosine of beta. The x component, now sometimes it gets confusing because you can't, the way that it's drawn right here, it doesn't look like it's has a particular relationship to beta, but we can kind of slide that guy over, and we could also say that this is x, the x component of E, and when we do that, we can see it's opposite, and then we know we would use the sine of beta. So we're looking for EX is equal to E times the sine of beta, and EY is equal to E times the cosine of beta, and they're both positive, so we're looking for that in our choices. So this one is not corresponding to it. The ones that have negative values are not corresponding to it. And process of elimination tells us that this is it, and it also matches with what we had determined would be the correct answers. For these particular problems, this is when we get into unit vectors. Unit vectors are nice to use. Keep in mind that the way that they're written, like vector A is written as AX times I hat plus AY times J hat. Similarly, B has been written with the X component times I hat plus the Y component times J hat. So the X component of A is 3, its Y component is 4. For B, the X component is -8, its Y component is 6. If I just tried to sketch these really quickly, I would have A would have a little bit more vertical than horizontal, so I might just kind of draw it like that. For B, it's in the second quadrant. This one has a little bit more X than Y, and so I draw it like this. Notice I'm not like being super careful, but I'm trying to get the general sense of what they might look like. So I've drawn the two vectors. Now I'm ready to find the angles. I might want to sort of sketch the x and the y components just to help me do the next part. I'm going to call this angle theta, and I'll call this angle alpha. And this is where we like to use the inverse tangent. Using the definition of the tangent of an angle is the y component over the x component. Actually, I want to go with the tradition that we've been using so far, and instead of that, I'm going to say it's the opposite over the adjacent. That's a better way to think about it. Okay, so for vector A, the angle theta is the inverse tangent of AY over AX. That's the opposite over adjacent. So it's the inverse tangent of 4 over 3. And I didn't have my notes here, so you're going to have to bear with me while I quick do my calculation on my calculator. So I get an angle of 53.1 degrees. I'm going to do the angle for alpha, tangent of -1. It's going to be by over bx. So it's the inverse tangent of 6 over -8. And when I get my answer when I get my answer for alpha, in this particular case, it gives me a negative reference angle because of the fact that one of those components was negative. What that is actually telling me is that this angle alpha is 36.9 degrees. I could say that alpha is 36.9 degrees measured clockwise from the negative x-axis, or I could, if I wanted to measure the angle from the positive x-axis, I'm going to call that beta. Beta would be equal to 180 minus alpha, well, plus alpha. It would be 180 minus, 180 minus 36.9. And so it would be 143.1, and this is measured counterclockwise from the positive x-axis. So a lot to think about there, but I think that this is the kind of thing that you might have done in trig, so hopefully it looks kind of familiar. The next thing I want to do is I'm told to add vector c. C is equal to a plus b. Adding vectors in unit vector form is quite easy. C is going to have an x component and a y component. The x component of C is going to just be the sum of the x components of A and B. And so that's going to be 3 minus 8 and 4 plus 6. And so I'm going to get minus 5i plus 10j. I can, if I want to find the angle that vector C makes with the horizontal. So vector C is in the second quadrant. It has a negative x component and a positive y component. I'm kind of running out of room, and I'm sorry, I'm going to have to go all over the place. If I say, I'm going to use gamma, is going to be the angle for C. It's going to be the inverse tangent, cy over cx. It's going to be equal to the inverse tangent of 10 over minus 5. So that's going to be minus 2. It's minus 63.4. So this is similar to vector B. So it's either 63.4 measured clockwise from the negative x-axis, or I can subtract 63.4 from 180, and it'd be 116 degrees, or 0.6, counterclockwise from the positive x-axis. It's two different ways that we can denote the direction. We can measure it relative to the negative x-axis and give the smaller angle, or we can measure it from the positive x-axis and give the larger angle. What is important is that when I get an answer like for vector B, I got minus 36.9. This is not a sufficient answer. I need you to be very specific and describe for me what exactly is the angle so that I know for sure the direction that that vector points in. Oh, I had more room. I didn't realize I had that extra. So sorry for the crammed notes on the previous slide. And then finally, we have, this is an example from the book. It was just another opportunity for adding vectors. So we have 3 dogs. They each are pulling with different forces in different directions. In this case, we're actually doing a 3-dimensional problem. We see that force 1 has an x, y, and z component. We want to be careful, and we notice that force 2 only has an x and z component, and force 3 only has an x and y component. If I want to add force 1, 2, and 3, I would do it like I did for the last one, but I have one more direction, the z direction. So I have f1x plus f2x plus f3x will give me the x component of the total force. And I'm going to do the same thing but with a y. And for the z, will give me the, so adding all those components will give me the total force. I'm going to go to the next slide to do the numbers. So the total force, I'm going to add my x. F1 has an x component of 10. F2 has an x component of minus 15. And F3 has a component of 5. So I have actually, so that's I. I'm going to do the y component. So F1 has a component minus 20.4. F2 does not have a y component. F3 has a y component of 12.5. And then for z, I have 2 from F1. I have minus 6.2 from F2. And I don't have a z component from F3. So this is how I'm going to just add these numbers to give me the total force. Notice I don't have, the x components have canceled out. And so for the y component, I have 12.5 minus 20.4. And so that's minus 7.9j. And then I have, for the z component, 2 minus 6.2, and that's going to be equal to, minus 4.2k. So the total force is minus 7.9j in the y direction, minus 4.2k. I think you might see that adding vectors with unit vectors is a lot easier. but we want to be able to do both methods. When we express a vector in unit vector notation, we don't always find an angle, especially in 3 dimensions. That angle is a little bit more meaningless because it's just not the same. We can't do the inverse tangent because here you can see that we're doing relative to y and z. And if we had an x component, it would really, like, we wouldn't know. How do we do it? We wouldn't have a ratio. We would have 3 things to deal with. So you can express a vector in unit vector notation, and that's considered you've completely described the vector. Or you can choose to express a vector as a magnitude and direction. So I know this was kind of long, but I tried to be very detailed so that you would feel more confident for Monday's assessment. And so I hope that this helps, and have a good weekend.